Bismillahirrahmanirrahim and Assalamu alaikum, my dear students. I welcome you all to the lecture number 11 of this online phase 2 of electric circuit analysis 1. Today we are going to study Norton theorem and maximum power transfer theorem. First of all, I will try to solve a practice problem and another question with you regarding Norton theorem, and then followed on we'll try and understand the new concept of maximum power transfer in an electric circuits. So I have taken this example from chapter number 4, and the problem number is practice problem 4.51. I'm going to solve it for you. In this we are going to use this figure. We have to find this Norton equivalent at two terminals. First of all, we have to consider terminal A and B in this circuit, and then the other part of the question is that we have to consider terminal C and D and find the Norton equivalent. Now, considering the first part of the question, terminals A, B, we get the circuit as this. I ignore the terminal C and D because I have to evaluate the circuit at these 2 points A and B, and I have to transform this entire circuit into its Norton equivalent. That means I need the Norton resistance across these two terminals and the current flowing from terminal A to terminal B, that is current, short circuit current or Norton current across the terminals A and B. So as you know that whether it is Thevenin resistance or it is Norton resistance, you know that we turn off all of the independent sources. When I turn off this voltage source, I replace it by a short circuit. This current source is replaced by an open circuit, and we find the equivalent resistance across the terminals A, B. You can see that now these two resistances are in parallel. I find the parallel equivalent of this, and I get to know that it is 2 ohms. Now the 2 ohm is in series with this 2 ohm, so we get a series equivalent of these two resistances. And now that across the terminals A, B, there's a 4 ohm resistor, and these two resistors sum up to become 4 ohm. So these two 4 ohm resistances are in parallel, so their equivalent would be 2 ohm. Please recall the rule that I told you. Whenever the same resistances are in parallel, their equivalent their parallel equivalent is always 1/2 of their entire value. If I had let's say 6 and 6 over here, the resultant would have been 3. As I have 4 and 4, the half of 4 is 2, so I get the Norton equivalent as 2 ohm. Now we move on to finding the Norton current across the terminals A and B. So I come across the same circuit. I put the 120 volt back and the 6 ampere current back in the circuit. Now what we do is we have to find the current flowing through the terminals A and B. So I can solve this circuit by doing source transformation. What I do is I do a source transformation over here at my left hand side and over here as well at my right hand side, since these are the terminals which I can. This is the terminal A, and the entire circuit would remain the same, and I'm not disturbing this terminal B, and I'm just taking the source transformation over here. When I get transform this, I get I is equal to V over R, and we put the values, and I get to know that I is equal to 20 ampere. Over here I transform the circuit, V is equal to IR, and just by plugging in the given values I get the new voltage value. And now you can see that these two resistances are in parallel. I take the parallel equivalent to simplify the circuit, and I get 2 ohm. So furthermore, I can again simplify this circuit by again taking the source transformation in this circuit. By transforming the source, this becomes 20 into 240 volt, and this 2 ohm resistance, which was previously in parallel to the circuit, now moves on to become in series with the circuit. So now you can see that I have a single loop. I can simply apply Kirchhoff voltage law to find the current across this loop. By applying the Kirchhoff voltage law, which states that the voltage gain across a loop or a circuit is equal to the voltage loss, I simply plug in values. 40 volt is the voltage gain. All the resistances are passive elements, and they always encounter a voltage drop, and the 12 voltage drop or 12 volt is a voltage drop because when I traverse this loop I go from positive or high potential to low potential, so that's why it's a voltage drop. And by solving simple arithmetics and using simple mathematics, I get to know that the current through this loop is I is equal to 3.5 amperes. So now we know that, and we have to find the current through terminal A to terminal B. So first of all, what I do is I find the V Thevenin, which is the 4 ohm V4 ohm, because these two elements are in parallel to each other, and please recall that parallel elements have the same voltage. So V Thevenin is 4I. I put in the value. Now I have to find the Norton current, the current that is flowing from terminal A to terminal B. By formula, it is IN is equal to V Thevenin by RN. Just by putting in value, I just found V Thevenin is 14 volt and RN is 2 ohm, and I get to know that the terminal A and B current is 7 ampere. Now I move on to terminal C and D. First of all, we'll find the Norton current. The rule is the same, just turn off all the independent sources. This is how I turn off, this is how I get to know. Now these two are in parallel, I take their parallel, and when I solve these two parallel, they are in series with this thing, and then this entire is in parallel to this 2 ohm resistance, and this is how I get to know the resistance across the offered to the terminal C and D. So the Norton resistance is, every single step has been done for you, and I get to know that it is 1.5 ohm. Now I move on to finding the Norton current. Norton current is found by looking in the original circuit. I use some source transformation over here, so I transform it just as I did in part 1, which was for terminals A and B. I take the parallel equivalent of these two to simplify the circuit. So I put in the values. This is 2 ohm, this is 20 ampere, and further on, as previously I did, I again do a source transformation over here, and I transform it into a voltage source. Now I have a single loop. I find the current through this loop, just simple as we did in the previous part. So after finding the current through this loop by using KVL, I get to know that the current through this is I is equal to 7 by 2. Every single step has been done for you. IN is by formula V Thevenin over RN. This means I have to find V Thevenin. So V Thevenin is the voltage across this terminal in the original circuit. So what I do is I have to find the voltage from this terminal to this terminal, which is the combination of this voltage source and this V2I. So this is how I find it. This is 12 volt because this 6 ampere was transformed into 12, and 2I, this is the resistance across this. So actually I had to find the parallel combination. These are the terminal C and D, so I have to find the parallel of these two combinations, and this is how I get to know the V Thevenin. Now once the V Thevenin is found, which is 19 volt, I can simply plug in V Thevenin value and RN value to find the Norton current that is flowing from the terminal C to terminal D. So this is how I got to know the value of current. Please try to solve chapter number 4 exercise problems, which are very much relevant to this. In case you have any problems, please do let me know. Now I move on to the last topic of this chapter, which is maximum power transfer. As the topic, the title elaborates that it is a technique by which maximum power can be provided or transferred to the load in the circuit. So we have to find the point at which, or the resistance level at which maximum power can be utilized by our load in the circuit. So it is for the maximization of power delivered to a load. And what is the methodology? I have to find the Thevenin equivalent of the circuit, and then from the Thevenin equivalent we get to know what would be the maximum power delivered to a circuit. For example, if I have a circuit entire, and I have to find the level at which the maximum power can take place, so first of all what I have to do is I have to transform the entire circuit into its V Thevenin and R Thevenin, which is the Thevenin equivalent of the circuit. And the point at which the maximum power is transmitted is RL is equal to R Thevenin. When the load resistance is equal to the Thevenin equivalent of the circuit, that is the point at which maximum power is delivered. So we know that P is equal to VI, which is further equal to I square R. So by plugging in value, I simply get to know that for this circuit, when I have to find I, it is the voltage applied V over R. I have only one voltage source, which is V Thevenin, and I have two resistance, R Thevenin and RL. The net resistance would be a series combination of these two. By plugging in this value in this formula, I get to know that P is equal to V Thevenin in whole square R Thevenin plus RL into RL. So maximum power, as I told you, maximum power transfer occurs when RL is equal to R Thevenin. Putting this equation 2 in equation 1, I get to know that the maximum power is transmitted this how, and the formula becomes V Thevenin square divided by 4 R Thevenin. and this only is applicable when we have RThevenin is equal RL is equal to RThevenin. Otherwise we will be using equation number 1 for evaluation. This is the equation number 1 for evaluation at any other point of power across a load resistance. Now, in order to further understand this topic, I will move on to example number 4.13. I have a circuit and I have to find the value of RL, this value at which maximum power can take place, and then after finding the value of RL, I have to find what is the actual maximum power for this circuit. So maximum power requires you to transform the entire circuit into its Thevenin equivalent across the terminals AB. Since RL is this, so the terminals AB must be these two. So what I do is I transform it into its Thevenin equivalent that requires the value of RThevenin and VThevenin. RThevenin is found by turning off the independent sources and by just looking into the circuit what Rn is being provided to the identified terminals. So these two becomes in parallel to each other. The parallel combination become this. Now the new circuit becomes this. This parallel combination is 4 ohm, which is now in series with this, and further in series with this 2 ohm resistance. So the RThevenin is very simple. You just get a series combination of these 3 resistors. Now moving on to finding VThevenin. I'll see the circuit as if now you can see that we have 2 loops. So I find the current flowing across each of the loop. For finding the current across each of the loop, we use Kirchhoff voltage law and mesh analysis. So V gain is equal to V loss. This is the voltage gain, and these two are the voltage drops. I1 flows through this, and through the 12 ohm resistance, you know that we have 2 currents, I1 and I2. I1 is the reference current, so it will be positive, and I2 is the loop current of the second loop, so it will be negative. As you know that I1 is in the downward direction and I2 is in the upward direction. That's why I2 has a negative sign. By simply rearranging the circuit, I get to know the equation. I get to know that this is the final state of this equation. Loop 2 has already a current source, and you can see that is 2 ampere, but the loop the current direction is downward. However, the 2 ampere current is upward, so it will be having a minus sign, and the reason is stated over here. So now we solve for I1 by putting value of I2 in this equation. I get to know that I1 is minus 2 by 3. Now actually we had to find VThevenin, which can be found by applying KVL at the outer loop. This is my outer loop. So this is V gain is equal to V loss. While going from low potential to high potential, this is a voltage gain, this is voltage drop, this is voltage drop, this is voltage drop, and obviously when I'm going from a high potential to low potential, VThevenin also becomes a voltage drop. By plugging in the values of the resistance and the currents, which is I1 and I2, I get to know that the current value, the VThevenin value is, I'm doing every single step for you so that there should be no confusion. VThevenin becomes 22 volt. Now we go back to finding the maximum power, which is, I already found that RThevenin is 9 ohms, so the maximum power can be transformed when RL, the load resistance, is equal to 9 ohm. And now for finding the maximum power value, we just plug in the value of VThevenin and RL, and I get to know that the maximum power transferred is 13.44 watt. That is it with this. We'll do another lecture on maximum power transfer theorem, then I'll provide you an assignment. In case you have any questions, please do let me know in the question answer session. Thank you very much. Best of luck. Allah Hafiz and take care.